you can go to the video made previously. That's where I'm at now, because we're going to make a couple of changes to it to simulate the motion of a projectile, where we don't just throw it straight up, but throw it at some kind of angle. So I will make a copy. I'll give it a name, projectile. Not. Okay, I'll just leave it as this. So what do we need to do? The main difference is that the initial motion, which was this vector here, the velocity vector, will no longer be straight up, straight vertical. So instead I'm going to rename this the initial, or velocity initial. If I try to run it now, it's going to complain. Scroll down, velocity initial is not defined. Yes, that is correct. So in the previous line, we have a couple lines here where we work on defining what that initial velocity is. So initial velocity is a vector, is a piece in the x, in the y, and in the z. So it's a vector. Well, initial equals a vector with an x component, call it vx, y component, call it vy, and we're not going to worry about the z direction. Okay, well, I need to define vx and vy. Now, usually when we're talking about throwing something, we don't say, oh, I've thrown it with so much horizontal and so much vertical motion. Usually we think in terms of a speed and a direction. So we have the direction equals, and this is going to be some angle, let's say 30 degrees. Initial angle in degrees. And we need to give it some initial speed. Speed equals, once again, let's go with 10 meters per second. So now the question is, how do I convert from this, which is one way of describing a vector, its size and direction, to the other way of describing its components, how much is in the x, how much is in the y, because x and y are independent. That's the power of vectors. So you can draw a little picture. If this is not familiar with you, look in the book. This is where we can use trigonometric functions, cosines and sines. So the x direction, that x piece, drawing the right triangle, is the overall size, the speed, times the cosine of the angle, the direction. Here's something I have to look up each time, so I'll let you watch while I look it up. I'm going to make a new tab over here. Tab to the right. The reason is I'm never completely sure if the glow script trig functions, sine and cosine, if they want the angle to be in degrees or radians, because that makes a difference. Glow script cosine. So here we go, math functions. And yes, it shows cosine. So reading through this, it doesn't say directly, but further down, it seems to be implying that, for instance, when I calculate the arc sine, arc cosine, and arc tangent, that the angles relate to pi, which implies radians. Okay, so that means we will have to convert from degrees to radians. And the conversion is that there are pi 0.1416 radians in 180 degrees, half a circle. And for y, same thing, except now we use the sine. Sine of the angle in degrees times 3.1416 radians per 180 degrees. Okay, let's save this. As a check, if I put the direction of 90 degrees, it should show everything going straight up. So let's just make sure we're okay with that conversion. Okay, so yes, so indeed, converting to radians was the proper thing. Okay, so change this back to 30 degrees. And we're going to do one more thing to help with the visualization. Is when we define the ball up here on line 4, I will say make trail equals true. What that will do is as a ball is flying through the air, it will show its path. Save early and often. So now this should throw a ball as if I threw it at a fairly shallow angle. There it did, and it showed the path. Now this is showing a few things. One is that my choice of range was a little too conservative. Looks like I could easily cut that down in half. And there we go. Now, since we chose to start at the origin, we're not really using the space very efficiently. That's okay. Dealing with that is fine-tuning that could be done later. I'll change the direction to a larger angle. There we go. Okay, so that was adding. We did not need to change the momentum or position update loop down here, but basically changing the initial velocity so that it is tilted at an angle instead of being straight up and down. So there are a couple more variations we can do on this. We've drawn the path of the ball, which is kind of like making a graph of the position in X versus position in Y, but we can do a more formal graph that has labeled axes so we can see how high the ball goes and so forth. Or we can make graphs of position and time or other things. And then we can start adding a force other than gravity that is trying to oppose, in a sense, the motion of the ball. So that will be for another time.